Welcome. Today we shall discuss Einstein's general theory of relativity. This theory has been regarded by many as the most beautiful of all physical theories. It is very novel and highly original. So let us see what are the essential physical principles that underlie this theory. Soon after Einstein formulated the principles of his special theory of relativity, he was bothered by two things. One is that he was absolutely sure that Newton's theory of gravity is inconsistent with the special theory of relativity, because the basic premise of Newtonian theory is instantaneous action at a distance. In other words, the gravitational influence of mass A propagates instantly to mass B and vice versa. And this is surely inconsistent with the principle of relativity, which says that no signal can propagate with a speed greater than the speed of light. But there were more problems. Einstein was bothered by the fact that Newton's theory is ambiguous about mass. According to Newton, mass is a quantity of matter. F is equal to ma. M is a certain quantity of matter. It represents the inertia. Whereas in special relativity, the mass should include all forms of energy. If you have kinetic energy or potential energy, that energy divided by c squared is equivalent to your mass. And you must include all types of mass in the theory. And Newton does not do that. Before the special theory of relativity was published in 1905, the great French mathematician Henri Poincaré wrote a paper in which he made the following extraordinary statements. Newton's laws need modification, according to Poincaré. And he said in that paper that there should exist gravitational waves, like electromagnetic waves, which propagate with the velocity of light. It is extremely important to appreciate that this paper by Poincaré predates the special theory of relativity. Now let's get back to Einstein's principle of relativity. Now this principle is clearly at odds with gravity, because Einstein's principle of relativity states that the laws of physics are the same in all inertial frames. All laws of physics, not just dynamical laws, but all laws of physics. But the fact of the matter is, since gravity produces acceleration, and since gravity is not an abolishable force, there can be no inertial frames in the universe, because no matter where you are in the universe, even in the vast space between galaxies, there is gravity, however small. Therefore, there is always acceleration. Therefore, one has to ask the question, how relevant is this principle of relativity if it cannot cope with the presence of gravity? Einstein said this, and it's rather eloquent. He said, it was most unsatisfactory to me that although the relation between inertia and energy, E is equal to mc squared, is so beautifully derived in special relativity, there is no relation between inertia and weight. So let me now explain what was it that Einstein was referring to and why he was bothered by this. Let us go to Newton's principle of equivalence. Newton introduced the concept of mass in two different contexts. He first introduced mass in his second law of motion, namely, force is equal to mass times acceleration. Therefore, the ratio of force divided by acceleration is a mass. And this mass is inertial mass. It is the mass that resists motion. This constant of proportionality is what is called as the inertial mass. But mass has two other roles to play in Newtonian gravity. Mass is actively the source of the gravitational field emanating from the body, and it reacts passively to the gravitational field produced by other bodies. So there is the concept of active gravitational mass and passive gravitational mass. Now let us call these MA for active gravitational mass and MP for passive gravitational mass. Now let's write some equations to make these concepts a little firmer. Let us say that there are two masses, 1 and 2. The force exerted by M1 on M2 is G, the active mass of M1, the passive mass of M2 divided with the square of the distance. On the other hand, the force exerted by the second mass on the first mass is G, the active mass of the second mass, and the passive mass of the first mass divided by the square of the distance. But Newton's third law says that action and reaction are equal and opposite. Therefore, these two forces must be equal to one another. Therefore, if I equate them, I get active mass of 1 divided by passive mass of 1 must be equal to the active mass of 2 divided by passive mass of 2, mass 3, mass 4, and so on. And since this ratio is the same for all masses, we might as well set this ratio equal to 1. And instead of making fuss with active gravitational mass and passive gravitational mass, let us introduce just one gravitational mass, which we shall call mg, m subscript g or m superscript g. So we shall no longer refer to active mass and passive mass. But we still have a problem. How is this gravitational mass related to the inertial mass? Remember, the inertial mass was defined in terms of F is equal to ma, whereas the gravitational mass is defined in F is equal to gmm divided by r squared. That m is the gravitational mass. So how are these two masses related? So let us consider a fixed mass, capital M, and a small mass, small m. And let us ask, what is the force exerted by the capital mass, capital M, on the mass, small m? And that is given by G, capital M, small m, divided by the square of the distance. So this is the gravitational force. What is the acceleration induced by this gravitational force? The acceleration is force divided by the inertial mass. Remember, F is equal to ma applies to all forces. Therefore, it applies to gravitational force as well. Therefore, the gravitational acceleration is this force divided by the inertial mass. So it is G capital M small m divided by r squared divided by the inertial mass of small m. And that can be written as the ratio of the gravitational mass to the inertial mass multiplied by G m by r squared. Now let us remember Galileo's experiments at the Leaning Tower of Pisa, where he demonstrated conclusively that the acceleration due to gravity is independent of the mass. Therefore, this acceleration due to gravity, which is force divided by the inertial mass, must be independent of the mass of the body. That is possible only if this ratio is 1. In other words, the inertial mass is equal to gravitational mass. This is what bothered Einstein very much. Newton introduces two masses in his theory, the inertial mass and gravitational mass. And then he goes on to say that these two masses must be equal. How do you know they are equal? Well, he spent years and years and years trying to do experiments to establish this equality. And he was able to show that the inertial mass is indeed equal to the gravitational mass to 1 part in 1,000 or so. Today we know that this equality between inertial mass and gravitational mass has been established to 1 part in 10 to the power 11. But that's a different matter. You are appealing to experiments to show that these two are the same numerically. But why should there be two masses, inertial mass and gravitational mass? This is what was bugging Einstein very much. In 1907, Einstein was asked to write a review article on the special theory of relativity for a very prestigious German journal. While writing this article, he was working at the time as a clerk in the patent office at Bern, the capital of Switzerland. And this is what Einstein writes. I was sitting in a chair in the patent office in Bern when all of a sudden a thought occurred to me. If a person falls freely, he will not feel his own weight. I was startled. This simple thought made a deep impression on me. It impelled me towards a theory of gravitation. What does he mean by this? Here is a man trying to climb a rock, and the rope breaks and he falls freely. And the mobile phone in his hand, everybody has to go have a mobile phone in their hand no matter what they're doing, the mobile phone also falls. And they fall at the same rate. They are both falling freely. And that man does not feel the weight of gravity when he is falling freely. Therefore, what Einstein felt was that a freely falling frame, this mobile phone or this man, is an inertial frame. There is no gravitational acceleration. Although gravity is not an abolishable force, if you could fall freely, then you can eliminate gravitational acceleration. And therefore, Einstein set up some thought experiment to extend Newton's principle of equivalence. And here are 4 experiments. Here is experiment number 1. Here is a lift attached to a rocket somewhere far away in intergalactic space. The rocket is fired and the rocket accelerates in that direction. There is a pseudo force acting in the opposite direction. A physicist inside this laboratory lets go a test particle, and the test particle will accelerate towards the floor of his laboratory. You will all agree that this must happen. Now let us do a second experiment. There is a laboratory on Earth. There is no rocket. There is no rocket being fired, but there is gravity acting in that direction. The same physicist lets go of a test particle, and the test particle falls and accelerates towards the floor. Now let's do a third experiment. The rocket in intergalactic space, the engine is switched off. Therefore, there is no acceleration due to the rocket. Now the physicist finds that if he lets go of a test particle, it remains stationary. It does not fall. Now let's do a fourth experiment. There is an elevator going in a shaft from the surface to the center of the Earth, a deep shaft. And let's cut the cable of the lift, and the lift will fall freely. Like our rock climber fell freely, the lift is now falling freely. The physicist inside the lift lets go a test particle, and the test particle will remain stationary. Now, Einstein's point was, by no experiment whatsoever can this person or this person tell whether he is being accelerated by a uniform gravitational field or whether he is being accelerated by a rocket engine. Similarly, by no experiment whatsoever can this physicist tell whether he is in a gravity-free space or whether he is falling freely in a uniform gravitational field. Therefore, Einstein extended Newton's principle of equivalence, which was the inertial mass is equal to gravitational mass. He extended it by saying that by no experiment whatsoever, mechanical experiment, optical experiments, electrical experiments, no matter what you do, you cannot tell the difference between a uniform acceleration and a uniform gravitational field. You cannot tell whether you're being accelerated uniformly by a rocket or by the gravitational field of a massive body. This seems very straightforward. But he deduced, Einstein being Einstein, he deduced two dramatic consequences of this extremely simple extension of Newton's principle of equivalence. The first was that the rate of ticking of a clock will depend upon the gravitational potential of its location. The second was that light will be deflected by gravity. So he did thought experiments and drew these two conclusions. Now, let me try to indicate one thought experiment, not due to Einstein, but due to Sir Hermann Bondi, the late Sir Hermann Bondi in Cambridge. And you'll convince yourself, if you listen to me very carefully, that if there is gravitational field, then it will affect the rate of ticking of a clock. Let us do this experiment. Here is the sun, and here is the earth. There is a conveyor belt. There is a pulley here, and there is a pulley there, and there is a conveyor belt connecting the earth and the sun. And there are 10 buckets that I hang in this conveyor belt. What is in these buckets? There are hydrogen atoms. What kind of hydrogen atom? In 5 of the buckets, I put hydrogen atoms in the excited state, blue atoms, and in 5 of the buckets, I put hydrogen atoms in their ground state. So these red atoms are all in ground state, these blue atoms are all in excited state. I prepare them that way. I manipulate the atoms so that they are in the excited state. Now, when bucket 1 comes to the sun, there it is at the sun, I arrange it so that the excited atoms comes from the excited state to the ground state, emitting a photon of frequency h nu is equal to E1 minus E2. Then I have a fancy mirror here which will reflect this photon to the earth, where there is another mirror, and the photon is reflected to the bucket number 6. In bucket number 6, there was an atom in the ground state. It absorbs the photon of frequency nu, energy h nu, and it goes to the excited state. Now you will agree that atoms in the excited state have more energy than atoms in the ground state. And since atoms in excited states have more energy, E divided by c squared, they also have more mass according to special relativity. Therefore, the conveyor belt will move. And so bucket number 2 will come to the sun. There it will de-excite from n equal to 2 to n equal to 1, emitting a photon. That photon goes to the earth and excites an atom from n equal to 1 to n equal to 2. So this belt will go on going round and round and round in a perpetual motion without my spending any energy. Surely you cannot do that. So the only reason you cannot do this can possibly be the following. Namely, when the photon that is emitted at the sun, when the atom de-excites from n equal to 2 to n equal to 1, by the time it climbs the gravitational potential of the sun and reaches the earth, its frequency has decreased. It has lost some energy. And therefore, it is not able to excite a hydrogen atom from n equal to 1 to n equal to 2. It doesn't have quite the energy that it needs. Therefore, the simple thought experiment tells you that if you have a gravitational potential, that it is an inevitable consequence that energies will be redshifted. That is the same thing as saying time intervals will be redshifted, or in other words, the rate of ticking of a clock will be affected by the gravitational field. Beautiful, beautiful experiment due to Sir Hermann Bondi. Now, let dt infinity, subscript infinity, is the time interval between two ticks of a clock when there is no gravitational field. So the clock is at an infinite distance from any massive body. Now, there is the same clock which I now bring near the gravitational field of the massive body, and the gravitational potential is u, Newtonian potential is u. The time interval is given by dt in a gravitational field is equal to dt infinity into 1 minus the gravitational potential divided by c squared. This is the result that Einstein deduced from his thought experiments, and it's not very difficult to deduce that. Therefore, the rate of ticking of a clock is determined by the gravitational potential. Stronger the gravitational potential, the slower the clock ticks. And when the gravitational potential is that of a black hole, then it stops ticking. We shall come to that later on. So to put it differently, time is walked in a gravitational field. The second conclusion that Einstein drew from his principle of equivalence is that light will be deflected by gravity. Einstein calculated that if there is a ray of light at a grazing angle to the sun, then it will be deflected ever so little, and the angle of deflection will be 0.83 arc second. A very small deflection, but nevertheless a measurable deflection. So he wrote in 1911, "It is highly desirable that astronomers concern themselves with the question brought up here, even if the foregoing considerations might seem insufficiently founded or even adventurous." So he says, even if my thought experiments are wrong, please go and do this experiment because it is worth doing this. Now, long before Einstein, before that, let me say this. In the summer of 1914, in August 1914, a German astronomer by the name Finlay Freundlich led an expedition to Crimea in the Black Sea to verify Einstein's prediction, because there was going to be a total solar eclipse on the 21st of August 1914. So Freundlich and his team left Germany towards the Black Sea. Unfortunately, what happened was, anyway, let me continue with what I've written here. Einstein was supremely confident of his result, namely, light will be deflected by 0.83 arc second. He wrote a postcard to his friend in which he said, "I do not doubt anymore the correctness of the whole system, whether the observations of the solar eclipse succeed or not." So, I don't care if you succeed or not, I'm absolutely convinced, he said. Unfortunately, as Freundlich and his team of astronomers were going towards the Black Sea, World War I broke out, and they encountered the Russian army. And Freundlich and his team were Germans, and Germany was at war with Russia, and therefore the Russian soldiers did not allow them to go to Black Sea, and Freundlich returned. But this was a blessing in disguise for Einstein. Long ago, Newton, in his book Optics, wrote this: "Do not bodies act upon light at a distance, and by their action bend its rays? And is not this action strongest at the least distance?" He asks a question. Is not light deflected by by gravity? Although Newton did not calculate the amount of deflection, his corpuscular theory of light will give for the deflection by the sun. A German astronomer by name Johann von Soldner had calculated the deflection of light by the sun in 1801 according to Newton's theory of gravity. And do you know what he found? He found that light will be deflected at grazing angle by 0.84 arc second, which is precisely the value calculated by Einstein 110 years later, in 1911. But here is the fact. In 1915, on 25th of November, when Einstein published his general theory of relativity, he predicted that the deflection of light will be double of what he had predicted in 1911. It will be 1.7 arc second, which is exactly twice the value he had predicted in 1911. If the war had not broken out, Freundlich would have gone to Crimea, measured the deflection of light, and he would have got 1.7 arc second, proving Einstein was wrong. And when Einstein subsequently did publish his theory of general relativity, it would appear to everyone in the world that Einstein was changing his result because of the experimental results, and the result of Eddington's famous expedition in 1919 may not have had the same impact. The expedition in 1919, Eddington showed that light is in fact deflected by 1.7 arc second, precisely as predicted by the general theory of relativity. So where did Einstein go wrong in 1911 by predicting half the value? If I remember, I will remark on this a little later. So we are in the year 1911 in our story now. Around that time, Einstein moved from Zurich to Prague in the Czech Republic today. And in March 1912, he had an extraordinary thought. He had concluded in 1907 that a clock in a gravitational field will tick slower. Therefore, time is warped. But in his theory of special relativity, he had shown that time and space are relative. What is time interval for one person can be space interval for another person, and vice versa. Therefore, he concluded, if time is warped by gravity, space must also be warped by gravity. This is a thought that had not occurred to him till 1912. So let us do a thought experiment. Here is a thought experiment that Einstein did in 1912. Here is a disk which is rotating about this vertical axis. And there is a cartoon of that by the famous physicist George Gamow in an article that he wrote long ago in Scientific American. In all his articles and all his books, popular books, George Gamow drew all his figures. He was excellent in drawing. And I'm afraid this is not a very good reproduction. So what you have is a rotating tent inside which there is a physicist. And the physicist is doing the following experiments. He has a bucket full of rigid rods, absolutely rigid rods. He places some of the rigid rods along the diameter of this rotating tent. And then he takes another set of rigid rods and places them along the circumference of this rotating platform. Now, this is what Einstein argued. If you're looking at it from an inertial frame, you will conclude that the length of these red rods, which are moving transverse to you, will be contracted, will be Lorentz contracted due to the principle of special relativity, because they're moving transverse to the line of sight. What does it mean? It means that the length of the rigid rod as measured by this physicist will not be the same as the length you infer of that rod from an inertial frame. On the other hand, these black rods which are placed against the diameter, they do not experience any transverse motion, and therefore their lengths will not be changed. Their length will be the same in the inertial frame and in the rotating frame. So convince yourself that these rods, when it is rotating, there will be no change in the length. There will be no Lorentz contraction. So, to summarize, as viewed from a non-rotating frame, an inertial frame, outside this rotating tent, rigid rods placed along the circumference will suffer Lorentz contraction, but rigid rods placed along the diameter will not suffer Lorentz contraction. Why should it bother you? Simply because, therefore, you will conclude that the ratio of the circumference to the diameter is not pi. Well, who told you ratio of circumference to diameter should be pi? Mr. Euclid in ancient Greece. Therefore, the person in the inertial frame will conclude that in the rotating frame, geometry is not Euclidean. The sum of the three angles of a triangle is not 180 degrees. Two parallel lines will meet at infinity, and the ratio of the circumference to the diameter is not pi. It can be less than pi, it can be greater than pi. Similarly, the sum of the three angles of a triangle can be less than 180 degrees, more than 180 degrees, but it will not be 180 degrees. The value it will have will depend upon the curvature. So, the important conclusion that Einstein drew in 1912 in the month of March is that in a rotating frame, the geometry is not Euclidean. Space is warped. What is the significance of a rotating frame? A person on the rotating frame experiences centrifugal force. But this centrifugal force is not a real force, because if I just step away from this rotating platform, I will not feel this centrifugal force. So this centrifugal force is a fictitious force arising due to the fact that I happen to jump on a rotating frame of reference. Another example of a fictitious force is Coriolis force. It's not a real force. So Einstein, therefore, said the following thing. If I am in a frame where there are fictitious inertial forces like Coriolis force and centrifugal force, I experience acceleration, and I find that the geometry is not Euclidean. Now, what Einstein said was the geometry of space-time, which encapsulates Einstein's theory of relativity, is pseudo-Euclidean. Remember Minkowski's space-time, which I discussed in the previous lecture. Although Einstein scoffed at Minkowski in 1907, by 1912 he had appreciated that Minkowski had in fact said a very deep thing, namely that the geometry of space-time, which is a collection of all events, past, present, and future events, the geometry is pseudo-Euclidean. The distance between two neighboring events is given by this formula with a minus sign over there. That's why it is not Euclidean, it is pseudo-Euclidean. For infinitesimal separations, this equation can be written as ds squared, where ds is the distance between two events which are separated by an infinitesimal distance in four-dimensional space-time, is c dt squared minus, in bracket, dx squared plus dy squared plus dz squared. Now, this result differs from Euclidean distance because in Euclid's geometry, that should be a plus sign. This is what Minkowski meant by saying that the geometry of special relativity, the geometry of space-time is pseudo-Euclidean in the special theory of relativity. Now listen to this very carefully. Einstein knew by 1912 that the rate of ticking of a clock depends on the gravitational potential at the location of the clock. The rate of ticking of the clock is the rate of ticking when there is no gravity multiplied by 1 minus u over c squared, where u is the Newtonian gravitational potential. In the absence of a gravitational field, the metric of space-time, if there is no gravitational field, the metric of space-time is of course given by this Minkowski's metric. This is what is called as a metric. Metric is to measure. Okay, the Latin word metric is to measure. So this is how you measure distances. According to this formula, ds squared is c squared dt squared minus etc. 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 In the presence of a weak gravitational field, this metric gets modified. Why does it get modified? Because we know this dt gets modified in the presence of the gravitational field. Therefore, the metric of special relativity gets modified in the presence of a weak gravitational field by this formula. Everything else remains the same, but the coefficient of dt squared is not 1, but is bracket 1 minus 2u by c squared. Therefore, Einstein concluded that the presence of the gravitational field modifies the geometry of space-time. This is the most important conclusion Einstein has drawn between 1905 and 1912. In 1907, Minkowski said, in the absence of gravity, the geometry of space-time is pseudo-Euclidean. Einstein concluded from the rotating disk thought experiment that in the presence of the gravitational field, the geometry of space-time will be further modified as shown over here. So the sentence that I want you to take away from here is that gravity modifies the geometry of space-time, which is an astonishing result. What has gravity got to do with geometry? So you're beginning to see how he was moving closer and closer towards his theory of general relativity. Now, in Minkowski's space-time geometry, there is no gravity in Minkowski's theory. Light and material particles travel in straight lines with uniform velocity, according to Newton's first law of motion. Now, how do you derive the equation of motion of a particle? Well, you can do any way you like, but in mechanics, what one does is that uses a certain variational principle. It doesn't matter if you have not studied this aspect of mechanics, but you can calculate the equation of motion of a test particle in the absence of any gravitational field. And you will find that the equation of motion is dx squared by dt squared is 0. In other words, the particle moves in a straight line with uniform velocity. There is no acceleration. Dx by dt is velocity, d2x by dt squared is acceleration. Therefore, the equation of motion of the particle is that the acceleration is 0 if there is no gravitational field, and the particle will move in a straight line with uniform velocity. Now, I go to a curvilinear coordinate system just because I want to have fun. I go to a rotating frame or some other curvilinear coordinate system. Now I derive the equation of motion for a free particle. There is no gravity. But at this time I'll find the particle does experience acceleration. d2x by dt squared is not 0. There is this beast sitting over here. What is that beast? There are these gamma, capital gamma, I, J, K. These are called Christoffel symbols. These Christoffel symbols are derivatives of the metric tensor, Gij. Gij is another way of saying c squared dt squared minus dx squared minus dy squared minus dz squared. You can call that as Gij and give the coefficients of the various terms. So the important thing to appreciate is that when I am in a curvilinear coordinate system, the particle experiences acceleration, which is determined by the derivatives of the metric. But there is no gravitational field. This acceleration arises simply because I am looking at this free particle in the absence of any gravitational field from an accelerating frame or from a rotating frame or from a curvilinear coordinate system. So the key point here is that this acceleration is pseudo-acceleration, just as Coriolis force and centrifugal force is a pseudo-force, it's a fictitious force. This acceleration arises simply by virtue of the fact that I happen to look at a free particle moving in the absence of a gravitational field from a curvilinear coordinate system. Okay, that's what I've said here. But this apparent acceleration, this acceleration is an apparent acceleration and is due to fictitious forces like Coriolis force and centrifugal force, because I happen to be looking at this particle and deriving the equation of motion from a curvilinear coordinate system. Okay, fine. Now, let's go back to the Cartesian frame of reference, no curvilinear frame of reference. There is no gravity. Particle will move in a straight line with uniform velocity. The acceleration will be 0. Now I turn on gravity. I turn on the gravitational potential, U. The metric will now be modified. Let the gravitational potential be rather weak. The metric will now be modified by this term 1 minus 2u divided by c squared. So this is the modification of geometry of the metric. So you may be mystified why I'm using the word geometry, because the way you define geometry is by measuring distances. And so the Minkowski metric is now modified because I've turned on the gravitational field. But I am in Cartesian coordinate system. Now I can go to a good book in mechanics and derive the equation of motion of a particle in a Cartesian coordinate system, but now in the presence of a gravitational potential U. Exactly as I had done before, but that was in the curvilinear coordinate system with no gravity. This time I am in the Cartesian coordinate system, but with gravity. And you know what I will find? I'll find exactly the same thing. I will find the particle experiences an acceleration, and that acceleration is determined by these Christoffel symbols. And what are these Christoffel symbols? They are derivatives of the metric tensor, which is defined by this equation over there. Don't worry about those details. There is a well-defined prescription for calculating all these Christoffel symbols. It's absolutely straightforward. So, let me repeat what I have said. This is the most profound conclusion that Einstein came to around 1913. In a general 1912, excuse me. In a general curvilinear coordinate system, a particle will experience an acceleration even in the absence of gravity. That is the acceleration. Taken to the other side, that is the acceleration. d2x by dt squared. Now, when there is gravity, the particle will experience an acceleration, and that is given by this. So, in a curvilinear coordinate system, when there are only fictitious forces but no gravity, I get an acceleration which is determined in terms of the Christoffel symbols. But when there is gravity, I get acceleration which is determined by these Christoffel symbols. And therefore, Einstein extended his principle of equivalence, stated it in a grand manner, that all acceleration derived from gravitational and inertial forces are metrical in origin. By that he meant that the acceleration is given by derivatives of the metric tensor. All acceleration derived from gravitational and inertial forces are metrical in origin. So what is the main conclusion? Einstein had concluded that the acceleration due to gravity is not due to any force that you call as gravity, that Newton called as a gravitational force. The acceleration due to gravity is metrical in origin because the geometry of space-time is not Euclidean. All right? Now, Einstein was ready to restate perhaps the most revolutionary statement ever made in the history of physics, namely Newton's first law of motion. Newton's first law of motion can be stated in two parts, slightly differently from what you have learned in school. It's the same thing. Every body moves in a straight line unless acted upon by an external force. So let me say that in the following way. There exists a standard motion of bodies such that if the bodies follow this standard motion, there is no point in looking for forces responsible for their motion. When do you stop bothering about forces and something being pulled by a rope? When it is moving with a uniform velocity. Newton disagreed with Aristotle. Aristotle said that there must be a reason for motion. Newton said, no, there need not be any reason for uniform motion. It is only acceleration that has to be accounted for. And he said that all bodies have a standard motion. And then he told you what the standard motion was. But the standard motion is a motion in a straight line with a constant velocity. So this is Newton's first law of motion. All bodies have a standard motion, and that standard motion is a motion in a straight line. Now, Einstein said, let me modify Newton's first law and make it even more revolutionary a statement. And he did this by appealing to the principle of equivalence, which I have just described. Namely, all acceleration due to gravitational forces and inertial forces are metrical in origin. So, instead of saying the standard motion is a motion in a straight line, he said a particle will follow a standard motion when all abolishable forces have been eliminated, that is, all forces except gravitation. Remember that gravity is not an abolishable force. You cannot get away from gravity no matter where you go in the universe. So, he says, live with gravity. Modify Newton's first law and state that all bodies will have a standard motion when there is gravity. The key word is standard motion. All bodies, the mobile phone or the rock climber, the planets, the stars, they will all have a standard motion. And what is the standard motion? The standard motion is free fall. Because whether it's a mobile phone or the rock climber or a television set or an astronaut, when they fall freely, there is no gravitational influence. So falling freely is the standard motion, not for moving in a straight line. What does falling freely mean? It could mean motion in a straight line, but it did not mean motion in a straight line. It's falling freely. The free fall trajectory is not a straight line, but a geodesic in space-time. What is a geodesic? It is the path which is the least distance between 2 points. If the piece of paper is flat, the geometry is Euclidean, then the least distance between any 2 points is if I draw a straight line between them. But if the paper is curved this way or this way, the least distance is not a straight line. It is a geodesic, which you have to calculate from curved geometry. That is what ds is all about. That is what the metric tensor Gij is all about. And geodesic, that is stated over here, that so if there is gravity, space-time is not Euclidean, and free fall is not motion in a straight line, that all bodies will move along a geodesic. And since it is a standard motion for all bodies, the motion is the same. So if I have a ball rolling down an inclined plane, the experiment that Galileo did in the Leaning Tower of Pisa, regardless of whether it's a ping pong ball or a steel ball or a platinum ball, they all experience the same acceleration. Why? Because they're all falling freely. And their motion is a geodesic in curved space-time. So Einstein's basic premise is when gravitational fields are present and they are unabolishable, space-time is a curved manifold endowed with a metric of the form ds squared is equal to Gij dxi dxj. If I am in a weak gravitation, if there is no gravitational field, this simply is c squared dt squared plus dx squared plus dy squared plus dz squared. Sorry, minus sign in one of the terms. So this is what you mean by the metric of a manifold. Now, if the manifold is curved, then this Gij's will not correspond to Minkowski's Gij, but will be different. So all bodies follow a standard motion when all abolishable forces have been eliminated, that is all forces except gravity, which you cannot eliminate. This way, Einstein triumphed. He eliminated the magic in Newtonian theory. He did not have to introduce an inertial mass and a gravitational mass only to identify them as being equal to be verified by an experiment. There is no need for all of that. All bodies experience free fall. That is described by, so the gravitational, the great discovery by Galileo, that gravitational acceleration is independent of mass, is now explained for the very first time. It is independent of mass because it's a free fall, and free fall is the same for all bodies regardless of its mass. So in 1912, Einstein returned from Prague to Zurich, back as a professor in the institute where he studied as a student. And there he met his old friend and classmate, Marcel Grossmann, who had by then become a professor of mathematics at the same Institute of Technology in Zurich. And a very important and very fruitful collaboration started. Einstein told Grossman that he was convinced that geometry has to be understood, gravity had to be understood in terms of motion in a curved space-time. So space-time is a four-dimensional space. When he was a student in Zurich many years earlier, he had studied, possibly from Minkowski himself, that the great Carl Friedrich Gauss had extended Euclid's geometry to two-dimensional curved surfaces, Gaussian geometry. So Einstein was convinced that what he needed was a four-dimensional version of Gaussian geometry, which was, as he had studied it, was only valid for two-dimensional curved surfaces. So he told Grossman, you must help me. He said, Grossman, you must help me or I will go crazy. Has somebody studied curved geometry in higher dimensions than two dimensions, for example, in four dimensions? Marcel Grossman said, give me one evening, I'll tell you tomorrow. So he spent the night in the library. Next day, Grossman informed Einstein that in 1854, Bernhard Riemann, one of the most distinguished students of Gauss, had generalized Gauss's theory to arbitrary number of dimensions. He also told Einstein of further developments of Riemannian geometry by Christoffel in 1869, and subsequently by Ricci and his brilliant student Levi Civita in Italy. So Einstein's basic premise was that when gravitational fields are present, space-time is a Riemannian manifold endowed with a metric of the form ds squared is equal to gij dxi dxj. He concluded from rotating frame experiment, thought experiment, that space is non-Euclidean in a rotating frame, therefore it must be non-Euclidean even in the presence of gravitational field. Because his elevator experiments told him you cannot tell the difference between the two. But why Riemannian manifold? Why not X or Y manifold? He had no answer for that. He said this seems to me to be the most reasonable assumption. So, when gravitational fields are present, space-time is a Riemannian manifold endowed with the metric of the form ds squared is equal to gij dxi dxj. Now Einstein concluded that the laws of gravitation must be formulated with an underlying metric of this form, and in a manner in which they are valid in any coordinate system, not just inertial frame of reference, but even in an accelerated frame of reference, because there is acceleration in the universe due to gravity, whether you like it or not. The underlying geometry of the physical world is Riemannian, with the requirement that locally the geometry must be Minkowskian or pseudo-Euclidean. Because locally I can abolish gravity. I cannot abolish gravity globally. If I'm in a rotating frame, if I jump out of the rotating frame, then centrifugal force is abolished everywhere. But you can't do that with gravity. You cannot abolish gravity. You can abolish gravity locally by freely falling, for example. But gravity is there everywhere. You have not abolished gravity. So he made the requirement that I must construct a theory of gravity. Please remember, this is not a theory of gravity. All that he has concluded by 1912, with the help of Marcel Grossman, is that gravity must affect the geometry of space-time. That in the presence of gravity, the geometry of space-time must be four-dimensional Riemannian geometry. And locally, the geometry must be Minkowskian. So in other words, locally, special relativity must always be correct. So in 1913, Einstein and Grossman wrote a joint paper. The first part of the paper was written by Grossman. The second part of the paper was written by Einstein. And in the first part of the paper, which was a brilliant mathematical exposition by Marcel Grossman, he had an extraordinarily lucid exposition of Riemannian geometry and its tensor calculus. Today, of course, there is no mystery about it. If you take a very elementary thing like Schramm series, I'm sure you're familiar with Schramm series. They have little books on vectors and differential equations and so on. They have one on matrices and tensors. There you will find a discussion of Riemannian geometry, the metric tensor, and everything that I'm going to say will be there. But at that time, it was not so well known. Now, Marcel Grossman in the first part of the paper outlined how one might formulate differential equations of the gravitational field in terms of invariance and covariance of the metric tensor. He introduced the Riemann-Christoffel tensor, which I shall mention over here. The Riemann-Christoffel symbol is given by derivatives of the Christoffel symbols. It has four indices, I, J, K, and L. It looks horribly complicated, but please be assured these are absolutely straightforward things, but one has to simply get down to it, take a piece of paper and pencil and write these things down. He also introduced the Ricci tensor, where you set two indices equal, or in other words, the Ricci tensor is a trace of the Riemann-Christoffel tensor. All this Marcel Grossman wrote in part 1 of this paper in 1913. Now, part 2 was written by Einstein, and it was very unsatisfactory. He was groping in the dark. He had great difficulty in formulating the laws of gravity, which will be valid in all frames of reference, inertial frames as well as in accelerated frames. Now, but he was approaching the problem in the following manner. One may ask three questions while formulating the laws of gravity. One, when can we say there is no gravitational field at all? Anywhere, there is no gravitational field at all. Secondly, you can ask, yes, there are material bodies. Yes, there is a gravitational field, but beyond the material bodies, at some distance from the material bodies, what are the equations that determine the gravitational field? Thirdly, you can ask, but what are the equations that govern the gravitational field in regions where matter is present? So these are the three questions that one should ask. And these are the three questions that Newton and people who followed him, like Laplace, asked. Now, the gravitational field in Newtonian theory is described by a scalar potential U. In the absence of any gravitational field, this potential, scalar potential U, is 0. So that answers the first question. Second question, there is matter, there is a gravitational field, but you are outside the matter. You are in a region where there is no matter. What is the differential equation satisfied by this gravitational potential? That is Laplace's equation. Del squared U is equal to 0. What is the third, you will ask, what are the differential equations that govern the gravitational potential when there is matter of density rho? That is given by Poisson's equation. Del squared U is equal to minus 4 pi g rho. So these are the three equations that tell you the laws of gravity. So Einstein said, how will these three laws be modified if space-time is curved and if you do not allow for propagation of gravitational influence at speeds greater than the speed of light? In the absence of gravity, particles experience no acceleration. Therefore, they move in straight line with uniform velocity. In a curvilinear system, coordinate system, particles will experience acceleration which are given by these Christoffel symbols. So, but you don't know whether you are experiencing an acceleration. You don't know whether it is because you are in a curvilinear coordinate system or whether there is really a gravitational field. How to tell? If there is no gravitational field, I must be able to go to a frame of reference in which all these Christoffel symbols vanish identically. It's like jumping off the rotating platform. You have abolished centrifugal force once and for all. So you can ask the question, so what is the necessary and sufficient condition to establish that it is really acceleration due to curvilinear coordinates and not due to gravity? Then, if there is no gravity, we should be able to find a transformation such that the Christoffel symbols, all the Christoffel symbols, vanish identically. Now, this is a well-defined mathematical question for which there is a rigorous answer. The answer is, according to Riemannian geometry, the condition that Christoffel symbols vanish identically is that this Riemann-Christoffel tensor must be equal to 0. This is equivalent to U is equal to 0 in Newtonian gravity. This is a necessary and sufficient condition. So this is Einstein's 0th law of gravity. So he said instead of U is equal to 0 being the statement that there is no gravitational field, the statement now is that the Riemann-Christoffel tensor must be equal to 0. Good. So I've got 1/3 of the way to my destination. Now there is gravitational field, but I am in a region where there is no matter. Well, in Newtonian theory, the differential equations that the gravitational potential obeyed was del squared U is equal to 0, Laplace's equation. So Einstein guessed that the generalization of this Laplace's equation is the vanishing of the Ricci tensor. Ricci tensor is the trace of the Riemann-Christoffel symbol. So he guessed that Rjk equal to 0 must be the generalization of del squared U is equal to 0. But you must verify this. How do you verify this? Now, first of all, this Rjk equal to 0 is a set of differential equations. It's a second-order differential equation, just as Laplace's equation is a second-order differential equation. There are 10 differential equations for 10 coefficients of the metric tensor Gij. So, Einstein's extension of del squared U is equal to 0 is a set of 10 differential equations which are 10 equations, the 10 coefficients of the metric tensor Gij. Now, here is the cross-check. You can ask, suppose gravity is extremely weak. Then you don't have to fuss around with Riemannian manifolds and all that. You know what the equation ought to be. So the above equation reduces to Laplace's equation in the limit c tending to infinity. So if I put c equal to infinity wherever it occurs, then you're going to the Newtonian limit. C equal to infinity means instantaneous propagation of gravitational influence, and you recover Newtonian gravity. So Einstein got 2/3 of the way. So he has found the extension of U equal to 0, which is the Riemann-Christoffel tensor is equal to 0, and he had found an extension of del squared U is equal to 0, which is the Ricci tensor is equal to 0, because this does go over to this when C goes to infinity. One can verify this if you are willing to spend 10 minutes with a piece of paper and pencil. Now let us ask, what are the equations in a region where matter is present? Well, in Newtonian theory, one relates the gravitational potential to the material density by Poisson's equation. Del squared U is equal to 4 pi g rho, where rho is the matter density. Now, that is Poisson's equation. Now, in general relativity, even in special relativity, density alone will not suffice to specify the distribution of matter and its motion. Because in special relativity, all forms of energy contribute to mass. Potential energy, kinetic energy, electrostatic energy, all forms of energy divided by c squared contributes to mass and therefore density. Therefore, in special relativity, one generalizes the notion of mass density to what is known as the energy momentum tensor. It is a 4 by 4 matrix with the first coefficient, 0, 0 coefficient, is rho c squared, and then there are the other coefficients which you can find in any book that is describing special relativity. So don't be lost in this because you don't know what is energy momentum tensor. All I'm saying is in special relativity, the notion of matter density has to be replaced by the notion of energy momentum tensor because all forms of energy contribute to mass. One would therefore be inclined to relate the Ricci tensor to the energy momentum tensor. Therefore, you may say the generalization of del squared u equal to 0 was that Ricci tensor is equal to 0. Therefore, Einstein could have guessed, so the generalization of Poisson's equation must be that the Ricci tensor is not 0, is not 4 pi 0, but is proportional to the energy momentum tensor, and the constant of proportionality is a certain kappa, which has to be determined. Great. So I have 3 laws of gravitational potential, gravitational field, and I have achieved my objective. Not quite. There is a serious problem with this guess. Why is there a serious problem? The problem arises because of conservation laws. There are conservation laws, conservation of momentum, conservation of angular momentum, conservation of energy, and so on. In special relativity, conservation laws follow from the divergence of the energy momentum tensor vanishing. In other words, to derive conservation laws, you have to calculate the divergence of the energy momentum tensor and set it equal to 0. And when it is 0, various conservation laws pop out. Now here is the problem. In non-Euclidean geometry, the notion of ordinary derivatives has to be replaced by what is called as covariant derivative. So ordinary divergence becomes covariant divergence. And the reason is very simple. In Euclidean geometry, in a piece of paper, if I want to set a derivative, I take the difference between, say, there is a field with 2 different values. I take the difference and divide by the distance. But if the paper is curved, that derivative has no significance. So you have to generalize the notion of derivative to what is known as a covariant derivative. You will find this in the Schramm series book by Murray Spiegel on matrices and tensors, for example, or any book that deals with elementary notions of tensors. So, in curvilinear coordinate system or non-Euclidean geometry, in special relativity, one would be dealing with covariant divergence of the energy momentum tensor equal to 0 to derive conservation laws. The guess that the Ricci tensor is equal to kappa Tij is a generalization of Poisson's equation will not work because the covariant divergence of the left-hand side is not equal to 0. The covariant divergence of the right-hand side is 0 because conservation laws require the covariant divergence of Tij is 0. Then the covariant divergence of the left-hand side Rij must also be equal to 0. But sorry, you can verify it, the covariant divergence of Rij is not equal to 0. But the covariant divergence of this animal, which is Rij minus half Gij times the trace of Rij is zero. This is known as Bianchi identity. Einstein did not know this. So for nearly 2 years, he was tormented. He made various attempts to generalize Poisson's equations to Riemannian manifold. And he simply couldn't do that because the covariant divergence of the Ricci tensor was not zero. So he even wrote papers where he was willing to abandon the notion of conservation laws and general relativity, an unthinkable proposition. But then he withdrew all that. Then finally, he realized that the covariant divergence of this is zero, and therefore the generalization of Poisson's equation is that not the Ricci tensor is equal to kappa Tij, it's the Ricci tensor minus half Gij minus R, where R is the trace of Rij. This is now called as the Einstein tensor. The Einstein tensor is kappa times Tij. Now you don't have any problem. The covariant divergence of the right-hand side is zero, and the covariant divergence of the left-hand side is also zero. So there is no problem. So all that remains before you open the bottle of champagne is to determine this constant of proportionality kappa. And that is easily done. You know that in the weak gravity limit, the metric is given by dA squared is c squared dt squared into 1 minus 2u by c squared, and these standard terms. You know that. Using this metric, one can find the limiting form of Einstein's equations. In the limit c tending to infinity, Einstein's equation reduced to these equations reduced to del squared u is equal to 1/2 kappa rho times c to the power 4. Where did this come from? By actually doing an honest calculation. Take this horrible set of nonlinear partial differential equations, let c tend to infinity, and lo and behold, this is what you get. That's what you get. What should you get? You should get del squared u is equal to minus 4 pi 0, which is Poisson's equation. That's what you should get. So we can now determine what is kappa by equating this right-hand side to this right-hand side, and you get kappa is minus 8 pi g divided by c to the power 4. So now we have got everything. We know all these things, and we have determined kappa, and that is Einstein's equation for the gravitational field. This is the general theory of relativity. This is the theory of gravitation. Now, let us make this comparison once again. On the left-hand side, I shall flash the 3 equations in Newton's gravity, and on the right-hand side, the 3 generalizations that Einstein made. The first equation is u is equal to 0. That goes to Riemann-Christoffel tensor is equal to 0. The second equation is Laplace's equation, del squared u is equal to 0. That goes over to Rijk, which is the Ricci tensor is equal to 0. The third is Poisson's equation, del squared u is equal to 0. That goes over to the Einstein tensor is equal to minus 8 pi g by c to the power 4 Tij, which is the energy momentum tensor. So, what is this theory telling you? This theory is telling you that gravitation is geometry of space-time. But it is more than that. The left-hand side tells you that the presence of mass modifies the geometry of Minkowski space-time, and the right-hand side tells you what is the motion of particles in this gravitational field. So matter modifies geometry, and geometry dictates what the motion ought to be. So it is a self-consistent thing. And the conservation laws are all automatically built into it because the covariant divergence of Tij is 0. This is not true of Maxwell's equations. You have to supplement Maxwell's equations with conservation laws. So when Einstein sent his paper for publication on the 25th of November 1915, this is what he wrote to a friend. Scarcely anyone who fully understands this theory can escape from its magic. Young Wolfgang Pauli, who was only 20 years old at that time, wrote as follows. This fusion of two previously quite disconnected subjects, the metric and gravitation, must be considered as the most beautiful achievement of the general theory of relativity. This fusion of gravity and metric leads to a satisfactory solution not only of the gravitational problem, but also of geometry. So this, my friends, is Einstein's general theory of relativity. Now, with that review of both the special theory of relativity and Einstein's theory of relativity, we are almost ready to embark on a discussion that you've all been waiting for, discussion of Chandrasekhar's theory of white dwarfs, neutron stars, pulsars, supernovae, black holes, and so on. So we needed this introduction to relativity. But before we get to this, there is one more thing that we must pause and understand. We must briefly recall the salient aspects of radiation from accelerated charges. I know you feel that I'm moving far away from astronomy, but I'm afraid this is essential, because at least at present, most of the information we receive from celestial bodies is from the electromagnetic radiation we receive from them at various wavelengths. So to understand pulsars, supernova remnants, quasars, active galactic nuclei, and so on, we must have some understanding of many radiative processes or mechanisms of radiation. Some of the processes we need to understand briefly are thermal bremsstrahlung, cyclotron radiation, synchrotron radiation from relativistic electrons, Compton scattering of electrons. And the kind of things we ought to know are the radiation mechanisms, the spectrum of radiation, the frequency content of the radiation, the characteristic frequency at which the radiation is emitted, the angular distribution of radiation, polarization, etc., etc. Therefore, the next lecture, the 16th in this series, I'm going to discuss radiation from accelerated charges. Before I conclude, I would like to once again request you, please, two things. One is, go to the website of the Astronomical Society of India, which you will find at the right-hand bottom of the poster, which I show in every video right at the beginning for several seconds. There, every Friday evening, when these lectures are uploaded to the YouTube channel, in that website, Dr. Sushant Kunal gives you references for that lecture and also a set of problems that you might like to try. Therefore, every Friday evening, do visit that special website of the Astronomical Society of India and look at the references that you may like to pursue. The second comment that I wish to make is something that I said earlier. I'm not very used to these online lectures. I would love to have your feedback. Therefore, please do take a few minutes to comment on each one of these lectures. After all, YouTube has that possibility of your writing your comments. You may like to ask a question. We'll see in the long run how to answer this question, perhaps in the website. So please take a few moments and enter your comments after viewing every one of those lectures. Thank you very much for your kind attention.